Okay, I just noticed that that continuous was misspelled. Okay, so what does continuous mean in your minds? Keeps going. Okay, are there any breaks in it? Are there any holes in it? No, it's completely smooth, continuous curve. Okay, so think about that. Now, in this picture, find the points at which the function below is continuous and where it's not. Okay? And so if you were asked to do that, between 0 and 4, where are the points where it's not continuous? I've kind of got them written here. At 1, at 2, and at 4. Okay? So there's a hole right there, and it's okay, it's fine there. It's defined there, it's not defined there. You move on. And so if you're looking at a graph, you want to look for those places where it breaks, where there's a hole, something like that. In calculus, we have a definition for continuity. Let's come down here. It would be important to maybe know this at some point. Continuity test. In order for something to be continuous, a function is continuous at an interior point, x equals c, if and only it meets these three conditions. This has to be true. F of c exists. So at that point, x equals 2, whatever, that has to be defined. The function has to be defined. The limit as you approach c has to exist. So there has to be a limit. Can't be limit doesn't exist because it's doing this. F of c has to be defined. The limit has to exist. And then those two things have to equal each other. The limit as x approaches c of f of x has to equal f of c. Okay, the limit equals the function value. If those three things hold true, then it's continuous at that point. So that's important to know. And sometimes just one of those things might not be true, and it would fail. Okay? Okay, and then we're going to look at some pictures of different kinds of discontinuities, places where it's discontinuous. So let's make this a little, is everybody through copying, or do I need to wait a little bit? Okay. You good? Okay. So I'm going to make this a little bit bigger so we can look at these pictures. Okay, right here, I don't know if you can see, but that dot right there at x equals 0 is closed in, and we've got this line. So at here, at x equals 0, this thing is continuous. Bless you. So in A, it's discontinuous. How about in B? What's there? It's discontinuous because at x equals 0, it's undefined. And right here, the same thing. On this line, it would be continuous. Could this be continuous if f of 0 were 1? And could this be continuous if f of 0 were 1 and not 2? Those are called removable discontinuities, because if it could be, if you could change it and say, well, if it were just equal to this, if f of x were equal to this, then it would be continuous. So sometimes we can remove it. And you'll see that, you'll find that when you can factor something and some stuff cancels out, you remove the thing that was discontinuous. So those are removable. How about this? Is there anything, I can't make this guy because there's two actual pieces of the graph. So this one is not continuous. It's called a jump discontinuity. These were removable. It wasn't. This one is continuous. Okay, and this is jump discontinuity. Over here. Long words. And you can't remove those. Okay? And how about this one? This is infinitely, it's at infinity, so there's no way to remove that. This is infinite discontinuity. And this one, like this sine curve or one of those trig, sine or cosine, this is oscillating, and you can't fix that either. So this is an oscillating discontinuity. Okay? So sometimes we can remove them, and we're going to learn how to do that. We'll learn how what that looks like as an equation and that sort of thing. But that's what those are. Jump ones, when they come in like this. Infinite discontinuity, when something's going up to infinity, there's no way you're going to change that. Or the oscillating, because up here close to zero, it's going up and down and up and down, and you can't get to a limit. So that's that. Questions on that? Okay, that got really big. We're going to go back down. All right. Now, continuous extension to a point. That's kind of like, it's more on the removing of a discontinuity. So let's think about this. If you had f of x equals sine x over x, that's this part right here. If you had that, is that continuous as it is? Can x equal 0? No. And so that would be this picture right here. Because at x equals 0, you've got a hole because x is not defined. Because if you were dividing by it, that's undefined, right? So everything else is fine. But you could extend it. You could change it if you made a new function and said, this is like a piecewise function, and said f of x is this for everything where x isn't 0, but f of x is 1 if x is 0. So we could kind of continue the domain. We could change it up a little bit. And so that's what that would look like, because you've defined another little piece. Okay? So you can sometimes do that. What we're going to be doing with that is doing some factoring. So let me show you an example of what we're going to do. Okay, so here's our example. I need to make it a little bit bigger so we can see it all. Show that f of x equals x squared plus x minus 6 over x squared minus 4 if x not equal to 2 has a continuous extension to x equals 2, and find that extension. So that sounds kind of confusing. Let's get it written as factors. On the top, that can factor to x plus 3, x minus 2. On the bottom, x squared minus 4 goes to x plus 2, x minus 2. So we're left with this, right? Okay. So our new function, x plus 3 over x plus 2, it's continuous at x equals 2, isn't it? That other one wasn't. This one up here, x not equal to 2, because if you put in 2 there, what happens to the bottom? Goes to 0. But our new function is fine at x equals 2, and the value at x equals 2 is 5/4. So by factoring, we removed that discontinuity and we extended it. We extended what we can do. So sometimes you can do that. You want to look at things and say, yeah, that's discontinuous. If you just put this guy in the calculator, what's it going to look like? Is it going to look like, what's it going to look like? Okay, put it in and let's see if it has a hole, if it has any problems. Put it in. And be sure when you do things like that, that you put the top in parentheses and the bottom in parentheses. Okay, is that what you got? This guy here, a rational function. Where is it? Discontinuous. -2. So it does have a hole at -2, but at 2, which we were talking about up here, it's fine. We removed that. We could see that we removed it. If you just put it in as it is, there's no problem over here. Literally, there is a hole. There is a discontinuity there, but in the calculator, it goes ahead and does that division and that factoring, and it removed it for you. Okay? Does that make sense? That sometimes you can factor it and remove that point of discontinuity, which was over here. Can't get rid of this thing, but we weren't even talking about that in the original thing. Okay? We good? Okay. So this was what that looked like. So you don't see that hole in the original, but that's what was actually there, and then we have that removed. Okay? All right, and the last thing that we want to talk about is the intermediate value theorem. You'll hear about it often. Sometimes they'll even just abbreviate and say IVT, but it says, let me make that a little bigger. If f is a continuous function on a closed interval AB, so that's brackets meaning A's included, B's included, from here to here, and if y sub 0 is any value between f of A and f of B, then y sub 0 equals f of C for some C in AB. Okay, a lot of letters, a lot of talk. What that's meaning, here we've got this distance between A and B. And here's f of A. That means if you plugged in A in the function, you get this value at f of A. And if you plugged in B, you get this at f of B. It's saying if that's true, and the whole thing is continuous in the whole interval, that for a C here, there's got to be a y value in between f of A and f of B that meets up with a C value that's between A and B. It sounds kind of common sense, really, doesn't it? It's saying in between these, if it's continuous, for any y value you pick here, it's going to be tied with a x value here. That's what that means. Okay? Now, the application of that, how we can use it, the way that I typically have seen it used, is if between the interval ends, you have a sign change. Like, if you were given an interval, say, let me see, from -4 to 8, and you were given a function, and you said, well, f of -4 is, say you got -24, and f of 8 was 136. Just throwing numbers out there, and we don't know what the function was. You had a sign change. It was negative, and then it was positive. What does that tell me? That there is exactly one, well, at least one root. There's one solution. If we change signs, if suddenly we're negative and then we're positive, if f of -4 is here and f of 8 is here, what does that mean this is? That's a solution. So if you're talking about the intermediate value theorem, and you know that at this end of the interval, if you plug that in, you get one sign, and at this end, you get another sign, then that tells you at least one place in there you've got a solution, you've got a root. So I know there's a question on the test about that, and I don't know that I have one in the homework, but we'll see it on the review that I chose, because I wanted you to see that application of that theorem. Okay? All right. So let's look at problems. Hold on. All right. Use the graph to identify an interval on which it's continuous. So we've got a lot of, I don't want to go big. Let me make this way. Okay, we've got some places where we have open circles and we have closed circles. And so we really need to look at our choices, because this is choices. And we can't just say, oh, it's from here to here. We need to look and see if it's true or not. Is it continuous? We also need to pay attention to whether we have a bracket or parentheses. If it's a parentheses, it means that's a boundary, but it's not really included. So if it doesn't work, it's okay. But a bracket means it has to work. So from -2 to -1. So here's from -2 to -1. They're both in brackets, but what's wrong with -2? It doesn't work there. So nix that one. All right, -3 and then up to +2. So from -3 to +2, we got some holes in there. That doesn't work. -2 to -1, but -2 is just a boundary. So -2 being a boundary, that's okay. To -1, does that one work? Yeah, that one is the right one. So you really have to look at all of those little intervals and see if they work, okay? And remember about that that's included and that's not. Okay, let me make this a little bigger too. All right, so this one. Use this to answer the following questions. Is f defined at x equals 2? So if we look at x equals 2, is it defined there? Open circle, so no. Oops. Is it continuous at x equals 2? No. Because remember, for something to be continuous, it has to be defined there. So that was pretty easy, but I didn't want you to see that. All right. Yes, sorry.
Why is it not defined as x equals 2 in this point? Oh, I was in there.
I was about to answer you, but you answered yourself. So, were you looking at?
I was looking at the graph, and I misread that. I was thinking, yes, I was looking at 1. So.
Okay, that's okay. At 1, it is defined. At 4, you're right. Okay. But that's good. I love it when you answer your own questions. That's perfect. If it's defined at x equals 1, it's defined. Is it continuous at x equals 1? No. So it can be defined there. And so what's the limit as x approaches 1 of this guy? It's up there at 5. But it's defined there. So they're different things. We have to get that kind of straight. Okay? All right. All right, use this graph to answer the question about discontinuity. Select the correct description of the continuity at x equals -2. So here's x equals -2. So this one says there's a discontinuity that can be removed by defining f of -2 equals 0. Discontinuity, here you can read them because I'm not reading well. Would it help us to say f of -2 is -2? That wouldn't help us, would it? Because that would put it down here. That doesn't help. There's a non-removable because it's not defined at x equals -2. What do you think? It's actually this one. If we defined f of -2 to be equal to 0, would that not close in that circle? That would close in that circle. Okay. I guess you're looking there and you can see that. Hey, that's good. All right, number 4. At what points is this continuous? Okay. It's discontinuous where the denominator is equal to 0. So if we didn't have this answer right here, how would we find that out? We would take the bottom and set it equal to 0. And in this case, we have to factor it. And so what are the factors of that? Okay. So these are the points where it is discontinuous. okay, at x equals 4 and x equals 2, but it says describe where it's continuous using interval notation. So we have to do this business. Think about 2 comes first. So on the number line, we've got 2 here, we've got 4 here. It's continuous all the way till we hit 2, and then it's continuous from 2 to 4, and then it's continuous from 4 to infinity. So that's where that answer, negative infinity up to 2, and then 2 to 4, and then 4 to infinity. And that's the way you would take care of everything in the world's fine except those points, 2 and 4. Yes, ma'am?
You said it's discontinuous with the denominator at 0?
Because you can't have 0 in the bottom of the fraction. Doesn't matter about the top. Top is fine. Okay, everybody good with that one? Yes, sir. No, never. Because you can't reach it. Okay. At what points is this guy continuous? Same, whoops, you'd like to see the problem. Same idea. You got to take the bottom of the fraction and set it equal to 0, which is pretty obvious. So this is where it's discontinuous. And so it's every point on the graph except 0. But if you have to put it in interval notation, you've got negative infinity to 0, 0 to infinity. If you didn't have to put it in interval notation, you could just say x, you could put all reals x not equal to 0 or something. But it asked for interval notation, so we need this. Okay? Yes. Yes. Because when you have a rational function where it's like a fraction, you're worried about the bottom because you cannot divide by 0. So anything that would make that go to that. Okay? All right. Let's look at this one. Find the following limit. The limit as t approaches 0 of cosine, cosine, I can't even read that, of pi over the square root of 17 minus secant 2t. Can we take the secant of 0? You've got your handy dandy trig sheet. Secant 0 is 1. If you have that trig sheet, it's helpful, right? So, okay, so there's no reason we can't just plug in on this limit, so let's do that. So we have the limit as t approaches 0 of all of that equals, okay, we've got pi over square root of 17 minus, the secant of 0 is 1, so we've got 1. Everybody agree with that? So that's pi over the square root of 16. Well, cosine's out here. Sorry. Okay. So the limit as t approaches 0, and now I got to evaluate this. So I've got the what? Well, but as t approaches 0, what happens to the 2? 2 times 0 is 0. So we're just taking the secant of 0. Okay. Maybe I'm shortcutting you on what I'm writing here. And so secant of 0 is 1, and 17 minus 1 is square root of 16. So then what do we have? We have the cosine of pi over what? 4. All right, cosine of pi over 4. You try to remember cosine of pi over 4, sine of pi over 4, they're the same thing, and it's always square root of 2 over 2. Okay, because pi over 4 is 45 degrees, and that's what it is. So That's the square root of 2 over 2. And in math lab, you know, it just kills me that they had the answer looked like that, because we don't typically leave a radical in the bottom. We always rationalize it. This is what I would want. Try that in math lab. It should work. Are you guys at all on your homework looking at it? Will you look at that problem? And number 6, if you have something like that, work through. See if it will take the square root of 2, if you get that problem, if you get one with pi over 4. That's what they have when it generated. But I would say this is a much more appropriate answer. Yes, ma'am. Maybe. For this first test, if you feel like you need it, you can have it after we look over the review. But you really do need to know that first quadrant of angles, pi over 6, pi over 3, and pi over 4. You really kind of need to know those, but we'll ease into it. Okay? All right, what did y'all find?
Are you going to run through
No.
the actual homework?
Yeah.
When you trade the problem?
Well, did it end up where you were doing pi over 4? Was that your angle or anything?
Oh, no, the homework is different problems.
I know. What angle did?
It'll be.
It's okay. It's okay. It's all right. Just know that I would put this in. If it tells you no, okay, so yours is going to be, and so will it take this? This is my answer. This is what I'm trying. Yeah, I do. You get 3 chances. So I would do this because that's the appropriate answer. All right, thank you for doing that. All right. Consider the following function and answer the following questions. All right, so we've got sine x over the absolute value of x. So you might want to throw that in your calculator so that you can figure out which graph this looks like. And notice that your window is negative 5, 5. That's your x-mins and max. And here's your y-min and max. So let's see what you get. So you want to, you can do second and the 0 key, and that gives you the catalog. And the first one is absolute value. There's another place for it. Math and then number. There's 2 places. I just use second 0 all the time. I don't know. Are you able to get that picture? Try a zoom 7 and see if that helps any. It shows up because that's a trig. So with zoom 7 you got, so which one of these do you get? See? Okay. So if we're looking there, okay, so we've picked out the graph. So you might make note that if it's a trig function in there, sometimes you need to do zoom 7 because that's a trig window. Sometimes it'll work without that, sometimes it won't, so maybe do zoom 7. If you want to match it exactly, then you could change it to these numbers and you'd get it, but you probably can tell. All right. If the graph appears to have a continuous extension to the origin, find a good candidate for the value at x equals 0. Okay. What I want you to think about is this continuous? Is this continuous at x equals 0? Bless you. No. Is it coming in this way? Do we have from the left and the right, it's totally different? So are we going to be able to remove that? Okay, so look at your choices. Which one makes sense? The best sense? Remember that continuity has to do with at a particular point or in a particular interval. So read D. The function cannot be extended to be continuous at x equals 0. It can be extended to be continuous at the origin from the right if f of 0 were what? 1. And or from the left if f of 0 were negative 1. So what it's saying is you could make it continuous coming from the right, just one separate thing, or you could make it continuous from the left because you could maybe remove that, but altogether it cannot be continued. Does that make sense? It's because it's that jump thing. So on this one you would choose D. C was the graph. D is that, and this would be 1 and that would be negative 1. So you'll have to fill those in. Okay? All right. Okay. This one, I picked this question when I picked it, thinking that it had an interval, and I guess I didn't read it real carefully. I was hoping that you would have this, and it would give you a particular interval, and you would test it and see if there were roots. It says use it to determine whether it has a solution or not. You can put it in the calculator and see that it has solutions. So at this point, that's what you're going to do. You're going to throw this in your calculator. It really is not a good indication to me of the intermediate value theorem. Put it in and see if it has solutions. If it does, find them and round the answers to 4 decimal places. So you're putting in y equals x cubed minus 3x minus 1. In your y1, you're putting the equation. The shortcut that I like to use, that I teach in college algebra, is to put y2 equal to 0. And then do second, calc, choose number 5, intersect, and go close to that point on the x-axis. Hit enter 3 times. All right, so you should get these answers here on that question. On the test, when we're talking about it, the question will say, and we'll do a review question on that, but it'll say something like, with this question in this interval, use the intermediate value theorem to show that there is a solution, or there isn't. And you'll just evaluate the endpoints of the interval and see if there's a sign change. So we'll do that on Thursday when we look at that. All right. So that, I think, is it for that one.